Okay, so in this video we will be explaining the Brownian motion as a stochastic process. Okay, so first of all, getting to the Brownian motion concept. Okay, so what is actually the Brownian motion? Okay, so if you look at water or any fluid, okay, for example, this is a fluid drop, you must have seen that there are particles, solid particles suspended inside it, and these particles regularly and randomly move, in some direction. Okay, it can be in any direction, okay, but they move in certain direction, and this motion is actually the motion of particles suspended inside fluid deals with Brownian motion. Actually, this motion of particles, this is random. Okay, this randomness is part of the stochastic process. Okay, because stochastic process is also random. We do not have like 100% surety that this particle will move in this direction, okay, or what will be the speed of this movement, or what will be the pace of this movement. Okay, so this is how the Brownian motion is a stochastic process. Okay, the stochasticity of the Brownian motion is because the motion of the particle is random, the speed is random, okay, the force is random. We do not know 100%, that we are not 100% sure that it will be in this speed or direction, and we don't know 100% about these parameters. Okay, so that is why the Brownian motion is considered as the stochastic process. Okay, so the Brownian motion, we have two kind of definitions to the Brownian motion. Okay, the formal and informal. So the informal definition for the Brownian motion is that the Brownian motion, also known as the Wiener process, okay, it actually models the random movement of particles suspended in a fluid observed under a microscope. So informally, let me write the definition. Okay, so it is a Wiener process, okay, and it models the movement of suspended particles inside fluid. Okay, and it is observed under microscope. Actually, this is the microscopic level of a study. Okay, so in mathematical terms, the Brownian motion is the random continuous time behavior of suspended particles of our system. Okay, and this system actually, it includes fluid and particles. Okay, so mathematical, it is the random continuous time behavior of a system, and this system is of the fluid and particle. Informally, the Brownian motion is also called the Wiener process, and it models the random movement of the particle suspended in fluid. Okay, as the motion is random, so that is why it comes under the umbrella of the stochastic process, because we are not 100% sure that in which direction or at what speed the particles will move. Okay, so So now let's get to the formal part of it. Now formally, the Brownian motion defined as B of t, okay, capital B of t, okay. The function is B of t where t is greater than 0 for any time instant greater than 0. So it is a Brownian motion process. This Bt is Brownian motion process where Bt, it represents a random variable which defines the position of suspended particle. Okay, so the particle position is defined by capital B of t. So at any instant time t, B of t, it represents the position of the particle. Okay, t on the other hand, it is a non-negative real number, okay, which means that t must be greater than or equal to 0, and it represents the time. Okay, and the start process, okay, the process starts at B of 0 is equal to 0. So at 0 time the position is at 0 0 of the particle. Okay, so these are the formal definitions or formal characteristics of the Brownian motion. Now Brownian motion with diffusion coefficient sigma square. Okay, now this diffusion coefficient actually, it represents that we are considering a scaled version of Brownian motion where the variance of increments is proportional to sigma square. Sigma square is the diffusion coefficient, okay, and this sigma square is actually a non-negative constant. Okay, I will later on define this diffusion coefficient. Okay, let me make another video, okay, because it is already like 9 minutes, so it will be easy for me to send it. So continuing the formal definition of the Brownian motion, the Brownian motion actually is a stochastic process denoted by capital B of t. Okay, this is the true denotation, okay, where t is greater than or equal to 0, okay, with diffusion coefficient sigma square. Okay, often it is sometimes denoted by v square. Okay, So if in exam or somewhere it comes v square, so don't be confused, the diffusion coefficient is sigma square, also denoted by v square. Okay, so the Brownian motion is a stochastic process, capital B of t where t is greater than 0, with diffusion coefficient sigma square if it satisfies following. Okay, so the first thing to satisfy is the initial condition. The initial condition is from where the Poisson process or the stochastic process starts. At t is equal to 0, capital B of 0 is equal to 0. Okay, it means that the process starts from 0. Okay, number second thing that must be satisfied is the independent increments. Okay, increment is like the particle is over here. Okay, so at certain time t, okay, t is equal to something greater than 0, okay, it is now at this position. Okay, so this is the increment. Okay, so for 0 less than or equal to t1 less than t2 less than t3 up to tn, the increments actually, the increments, okay, the increments capital B of t2 minus B of t1. So initially this position, this is B of t1. Okay, the second position is B of t2. Similarly, after it moves to this position, or even if this position, this is B of t3 and so on. Okay, so the particle will move in these small increments. Okay, so the increments B of t2 minus B of t1. Okay, similarly B of capital B of t3 minus B of t2 and so on, these increments are independent random variables. Okay, these are random. This satisfies the condition that indeed the process is stochastic. We don't have 100% surety that the particle will move in such direction. Okay, also we do not know that the next position of this particle will be exact this place. Okay, the direction will be this place, and also we do not know about the pace of the process. Okay, so these are random variables. Okay, what does it mean? It means the proper meaning of this independent random variable is that the future movements, actually the future movements does not depend on the past movements. Okay, for example, the from t1 to t2, the position of the direction of the placement is this, but in the next one the direction is about 90 degree, so we do not know exactly what will be the next position of the suspended particle. Okay, so this exactly shows the independent increments, which means that the future increments or the future displacements or the motions, it will not depend on the past motions. From the past motion you cannot predict the future. Okay, now the third one to get satisfied is the normally distributed increments. Okay, what does this thing means? It means that the increments are normally distributed. Okay, the increment is, for example, for all s and t greater than or equal to 0, the position for s plus t minus b of s. S is the initial position and s plus t is the next position. So if we subtract the initial position from the next, it gives us the perfect increment of that. So this increments follows the normal distribution with mean of 0 and the variance or the variance of a sigma square t. Okay, so it means that the mean of these increments is equal to 0 and variance is equal to sigma square into t. Now this variance sigma square t, it means that the displacement actually it grows linearly with time t. Okay, so these three are the the conditions for the formal definition of the Brownian motion. The first condition is that at any time t0, the first location or the process start from scratch 0. Okay, then we have independent increments. Independent increments means that the future increments or the future displacements, it will not rely upon the past increments or past positions. Okay, then all these increments, because the displacements occur in small increments, okay, so these are normally distributed with the mean of 0 and variance of sigma square t. And this variance of sigma square t means that the particle grows or the distances grows linearly with time t. Okay, I will continue in the next video. Okay, so this was a formal. In the next I will explain the parameters and variables that are studied over here. Okay, thank you. So in this video we will define and explain the key parameters and variables of the Brownian motion. Okay, key parameters and variables. So the first one is b of t, which is the main thing, okay, which denotes the Brownian motion. Okay, so this is the value of Brownian motion at any time t. Okay, t is actually time and it is non-negative. It must be greater than or equal to 0. Okay, the next thing is sigma square, which is the diffusion coefficient. Okay, diffusion coefficient. Okay, what does this thing means? It controls speed or the spread of process. Okay, for example, this is a fluid. Okay, fluid drop. Okay, these are the suspended particles. Okay, so for any particle, this one, okay, the displacement it has in any direction. Okay, so the pulse of it or the speed of it, actually it is defined by this diffusion coefficient. Okay, we know that diffusion is actually the travel of the suspended particle in some fluid. Okay, the fluid may be air or the any liquid. Okay, so for example, these are some particles. Actually these are in high number over here. Okay, we know that, and this is some liquid. Okay, so these particles actually travel from air into this liquid. Okay, so this travel of this particle, okay, into the liquid, actually this phenomena is called the diffusion. Okay, these are two kinds of travel, diffusion and osmosis. Diffusion occurs from high concentration to lower concentration. Okay, so this is diffusion. Osmosis, on the contrary, it occurs from, it is the reverse of the diffusion. The particles travel from lower concentration towards the higher concentration. Okay, so that is osmosis. Okay, so this is the diffusion coefficient, which defines the speed and spread of the process. Okay, and we have normal distribution n with mean of 0 and the variance of sigma square t. Okay, so this is normal distribution. Then we have S and T. Okay, these are 2 points. Okay, or 2 time stamps or time points. Okay, B of S plus T minus B of S, this is actually the random increments. Okay, these are the increments of process over time of length t, and the starting time is denoted by S. Okay, so S is the starting time, this is the starting time, and this T is the length of process time. Okay, so these are actually the parameters and variables that we will be following in the Brownian motion. Okay, now we have mean and variances actually. Okay, so the mean or the expected value of the B of t, this is equal to 0. Okay, because the Brownian motion actually, it is followed by the normal distribution with the mean of 0 and variance of sigma square t. So the mean of the Brownian motion is equal to 0. Okay, while the variance of this Brownian motion is equal to sigma square t. Okay, mean is the expected value of B of t, and variance is the spread, sorry, not the spread, actually the differences between the 2 bytes. Okay, and it increases linearly because it is sigma square t, so it is directly proportional to the time t. So it means that with time t, the variance, it increases linearly. Okay, so in the next, inshallah, we will be doing the transition probability density function, the diffusion equation, and then some physical interpretation. Okay, so in this video we will be carrying forward the Brownian motion. Okay, so today we will be studying the transition probability density function. Okay, or the probability density function of B of t. Okay, where B of t is actually the location, or what we can say that the current state of the particle. Okay, Brownian motion at time t. As the Brownian motion it is done in steps. Okay, in incremental steps. So this is the actually the position of the particle among these steps. For example, this is a graph. Okay, this is time and this is the position of particle. For example, at 0 it starts from this position. Okay, So randomly it is moving like this. Okay, so B of t is this thing. It is the position of this particle at each time t. Okay, so now the distribution that this B of t will follow, this is equal to f of x such that t, and it is equal to 1 divided by under the root 2 pi sigma square t multiplied by e raised to power r exponent of minus x square divided by 2 pi square t. Okay, and why is this? It is because it follows the normal distribution with 0 mean and pi square t as the variance. This is the mean, okay, and this is the variance of B of t. This is the mean of our expected value of B of t, which is equal to 0. Okay, so in this thing, x is the possible value the Brownian motion can take. Okay, f of x such that t, this is the PDF at time t, which is the probability density function. Okay, and this thing, this is normal distribution which is centered at 0. Okay, and the variance is equal to pi square and multiplied by t. Okay, so this is actually the transition probability density function. Now we will continue to the conditional probabilities in Brownian motion. Just like we did in the Poisson processes, so we will also do the conditional probabilities in the Brownian motion. So a standard Brownian motion, actually standard Brownian motion, which is B of t such that t is greater than or equal to 0, this is, we know that this is a stochastic process with 5 main qualities or properties. I will define all these 5 properties. The first property is that the start of the Brownian motion, it is equal to 0. So it is starting from 0. The second property, which is the independent increments. Okay, independent increments. As the process is stochastic, so the next step will not be relying on the previous step. So all the steps, all the increments are independent of each other. Okay, so it can be defined as, like, for any time between 0 and t, the increment which is stated as b of t minus b of s. Okay, this is the starting time, b of s, and t is the next time interval. Okay, so the increment is equal to b of t minus, this is the position at time t and this is the position at the starting time s. Okay, so this increment is independent of the past motion. Okay, it will not depend on the past motion. Now the third is the stationary increments. So the third one is stationary increments. We know that increment is b of t minus b of s. Okay, so by stationary increments we mean that the distribution of b of t minus b of s, which is the increment, depends only on t minus s. Now what is t minus s? T minus s, for example, we are doing it in two steps. Okay, this is the b of 0, which is starting at 0. Now this is the first one. Okay, this is b of 1. This is time. Okay, x-axis for shows the time. Okay, and y-axis actually it shows the position. Okay, b of t. Now this is b of 1. Okay, now this is b of 2. Okay, so the increment, which is b of 2 minus b of 1, actually it is only depend on 2 minus 1 time, only on this time frame. This is only significant in this time frame. It does not depend on this time, it does not depend on the future time. It only depends on the time between these 2 minus 1, the time between the clock time 2 and clock time 1. Okay, I hope you understood it. Let me know if you have any question regarding this thing, the b of 2 minus b of 1 dependency on t minus s. Okay, these two here, actually this is t and 1 is s. Okay, so the increment will depend on only the time duration in between, which is equal to t minus s. Okay, it will not depend on t plus 1 beyond t, and it will not depend on below the s, for example s minus 1. Okay, it will only be significant in t minus s. It will depend on t minus s only, in which the motion actually happened. Okay, the motion did not happen on time 3, it did not happen on time 0. The motion happened between 2 and 1, so it will depend on 2 minus 1 time, the time in between 2 and 1. Okay, this is the third property, and it is stationary increment. So by stationary we mean that we have a significant point actually. Okay, and the Brownian motion depends on only those 2 points, which are t and s, in this case 2 and 1. Okay, so that is why we call it stationary increments. Now for the next, actually, for example, here it happened to be the third one. Okay, this is time 3. Now if you want to consider b of 3 minus b of 2 increment between these two, it will depend on 3 minus 2. Okay, it will not be depending on 1. So that is why we have stationary increments. Okay, between two exact lapses or between two exact timestamps. Okay, now the fourth property is that b of t follows the normal distribution. Okay, with the mean of 0 and pi square t as the variance. Okay, and b of t minus b of s, the increment, actually it follows normal distribution with the mean of 0 and t minus s as the, just like we discussed over here, the stationary increments. Okay, so it follows normal distribution. Okay, for Brownian motion at time t, it follows normal with 0 and pi square t, and the increment, it follows normal distribution with the mean of 0 and the variance of t minus s. Okay, this is the fourth property. And the fifth property is the continuous path. Okay, so it means that this b of t, which happens to be, making something graph like this, okay, this is continuous, just like we did it in this graph. It is continuous, it is not discrete. Okay, it is continuous in time t. Okay, so these five are the properties of the Brownian motion. Okay, and we need to address this before we go to the conditional probabilities. Okay, in the next I will do the conditional probabilities. Okay, and then I will solve a question or two based on the conditional probabilities of Brownian motion. Okay, so now we will actually explain the key concept in conditional probability. And this conditional probability is in the Brownian motion. Okay, remember that in the Poisson distribution or Poisson process, we had the probability that x of t is equal to n, such that x of t plus 1 or t plus 2 is equal to z, for example. Okay, this was conditional probability over here. I will quote a regular example. Okay, probability that x of 1 is equal to 5 such that x of 3 is equal to 12. Okay, we found the conditional probability in, this is the conditional probability in a Poisson process. Okay, but now we will do it the same concept in the Brownian motion. Okay, so in Brownian motion, we have probability that b of t is greater than level A such that p of s is equal to b. What does this statement actually mean? Okay, this means that what is the probability of Brownian motion exceeding level A at time t, where it was at level B at time period s. Okay, this s is time period, t is time period. Okay, this A is level and B is level, which means that we are finding the probability that b of t, the Brownian motion at time t, is greater than greater than level A, such that at time s it was equal to level B. Okay, so for this we will use the incremental property and conditional distribution. Okay, so the first property that we will use is the incremental property of Brownian motion. We know that the Brownian motion actually happens in incremental form. and these increments are stationary. Okay, so mathematically I can write it as P of t is equal to B of s plus P of t minus B of s. Okay, let me write it in the graph method, because you are already, you are confused in the probability in Python also regarding this equation. Okay, so we have two time factors, okay, or two time stamps. Okay, one is s. Okay, s is the time period from which the Brownian motion actually starts. This is B of 0. Okay, we know that B of 0 is equal to 0. This is the first property of the Brownian motion, that it starts from 0. So S is the first time period that the Brownian motion, the particle actually reaches some level. So this level is B of S. Okay, then it happens another time period which is t. Okay, this x-axis shows the time period, okay, time, and this shows the level. Okay, b of t. Okay, so here we have B of t. Okay, so this B of t is actually equal to B of s, which is this one, okay, this level, plus the difference between these two levels. Okay, so B of t, this thing, it is equal to B of s. Why I am considering B of s? Because it happens in steps. So this step is including s and t. Okay, this byte is between s and t, where s and t are the time stamps. Okay, s is the starting time and t is the next time. Okay, so B of t, if quantitatively checked, it is equal to B of s plus the difference between these two. Okay, this is equal to this plus the difference between these two, which is equal to P of t minus P of s. Okay, so this is the incremental property that we are using over here. Okay, the second thing that we are using over here is the conditional distribution. Okay, so given that B of s is equal to B, then B of t such that B of s is equal to B, it follows normal distribution with the mean of 0 and variance of t minus s. Sorry, this is not equal to 0, the mean will be B, because it starts from B. Okay, we are given that B of s is equal to B. Okay, so the mean will be B and the variance will be equal to t minus s. Okay, this is the conditional distribution for the conditional Brownian motion. Okay, now we will use these two properties, the incremental property and the conditional distribution or the normal distribution. Okay, and we will come up with an equation to find the conditional probability. Okay, so the Brownian motion, if it starts with timestamp s and it is equal to B, okay, it follows normal distribution with the mean of B and the variance of t minus s. Okay, so B here is mean and t minus s here is variance. Okay, so I will now quote an example. Okay, So we want to compute the probability that b of 4 is greater than 3 such that b of 0 is equal to 1. Okay, now at first what we will do is we will find t and s from this thing, and we will find a and b from this thing. Okay, so the probability that b of t is greater than a such that b of s is equal to b. Okay, now comparing this, for example, this is 1 and this is equation a that is given to us as general or generic form. Okay, now consider this and compare this with this, the upper one 1. Okay, so we will say comparing a with 1, what we get is we get that t over here is 4. B of t is greater than a, so b of 4 is greater than 3, so t is equal to 4. Okay, a over here is 3, s over here is 0, and b is equal to 1. Okay, so according to conditional distribution, 1 follows normal distribution. Okay, and we know that the b of t such that b of s is equal to b, it follows normal distribution with b and t minus s. Okay, so using this distribution, what we have is we have b, so the normal distribution that it will be following is 1, and t minus s is over here is t minus s is 4 minus 0, so it will be following normal distribution with the mean of 1 and variance of 4. Okay, now we will use the z is equal to x minus mu divided by under the root standard deviation. Okay, standard deviation is what we call the variance. Okay, and x minus mu, so x over here, it is b of 4. Okay, mu over here is 1, this is mu. Okay, this is the mean is 1. Okay, variance is 4, so this is equal to 4. So we will find the z value, okay, from this. So z is equal to b of 4 minus 1 divided by under the root standard deviation or variance. Okay, so b of 4 over here minus 1 divided by under the root 4 is equal to z. Okay, now the probability that b of 4 is greater than 3 such that b of 0 is equal to 1 is equal to probability that z is equal to z is greater than P of 4 minus 1 divided by under the root this. Okay, now putting B of 4, we know that B of 4 is equal to 3. Okay, so it will be equal to probability Z is greater than 3 minus 1 divided by under the root 4. Okay, so it will be equal to probability that Z is greater than 2 by 2. So 2 will be cancelled with 2, so it will become 1. Okay, so it will be equal to probability that Z is greater than 1. Now to employ this Z value, we have probability that Z is greater than 1 is equal to 1 minus the normal distribution of 1. Okay, which is equal to 1 minus this thing. If looked in table or in online, it is equal to 0.84. Okay, so 1 minus 0.84 is equal to 0.158. Okay, so the probability that B of 4 is greater than 3 is such that B of 0 is equal to 1 is equal to 0.158 or 15.8% chances. Okay, I will also do other examples, so I will explain this normal distribution Z and everything again. Okay.